Nuclear magnetic resonance NMR deals with the magnetic properties of hydrogen or carbon nuclei. The hydrogen NMR is used more than the carbon 13 NMR because the proton spectra are much easier to obtain than the carbon 13 spectra. Also, the carbon 13 isotope is present in about like 1% of carbon atoms, and that makes it difficult to detect. The hydrogen isotope is almost 99% more abundant, and it is easier to observe. Now, the term proton that we are going to use throughout, it means a hydrogen atom. Precisely in the NMR, we are talking about hydrogen 1 isotope. Although we do have hydrogen 2 isotope, which is a deuterium, and hydrogen 3 isotope, which is a tritium, and both of these are NMR active, but both they observe at different frequency than the hydrogen 1 isotope. And also hydrogen 1 isotope is way more abundant and more common than the deuterium or the tritium. So this is why we're going to focus on hydrogen 1 NMR. So both hydrogen and carbon 13 have their nucleus exhibit magnetic properties in presence of the magnetic field. So their nucleus spins. And we're going to give those numbers in there. These are quantum numbers for the spin of their nuclei, +½ and -½ +½ is when the nucleus spins with the magnetic field. It's in the same direction of the magnetic field. And -½ is when the nucleus spins opposite to the magnetic field. When we take a proton or carbon 13 in nucleus and we place them in an external magnetic field, their nuclei is going to start to spin. Another term we give is resonate. So it's going to start to resonate in there, and it will only absorb the radio wave radiations whenever the energy of the photon is equal to the band gap between the two spin states. We know that the spin state, which is with the magnetic field, this is lower in energy than the spin state against the magnetic field. And the difference in the spin state is equal to delta E. So when delta E is equal to the energy of the photon, then in this case, the nuclei will absorb the radio wave radiations. And when it does, this is going to cause a spin flip. So the nucleus is going to flip its spin, and you're going to see a signal in the proton NMR. The proton NMR spectra is the plot of the intensity of the signal versus the chemical shift. The chemical shift we represented by a sigma, and the scale of the chemical shift is from 0 to 12 parts per million. Units are in parts per million. And this is what's going to tell me where each different hydrogen is going to lie in the proton NMR spectra. It's going to absorb in the proton NMR spectra. Now, proton NMR is to detect different hydrogens in different environments. So if you have a carbon that does not have a hydrogen, you're not going to see the signal of it in the proton NMR. You will see it in the carbon 13, but not in the proton NMR. Now, when you run a proton NMR spectrum, you need a reference. And that reference is just to adjust the signal of the other protons based on the 0 parts per million, which is basically the TMS. This is tetramethylsilane. We use this reference because it's CH3s, they do have hydrogens, and those CH3s, they absorb at 0 parts per million. So if you're working with an NMR spectra and you see a signal at 0, please neglect that because this is the TMS reference there. Now, the intensity of the signal is going to represent the number of hydrogens that correspond to that signal. So this is why it's very useful, and we can know how many hydrogens are there for every signal. The process is called integration. We're going to go over that as we proceed. There are two regions in the proton NMR, and those regions, they vary where they are. The regions are called the upfield region and the downfield region. So let's explain the theory behind the upfield and the downfield region. Let's say, for example, you have your hydrogen nuclei that is spinning in there. Now, a nucleus, because of the Earth magnetic field, they do have a spin. They do exhibit a spin. If there is an external magnetic field or if there is no external magnetic field, they are spinning. Okay. Now, of course, when you apply a magnetic field, they are going to spin more. So if you place them in presence of an external magnetic field now, they're going to go ahead and spin more. So if you look at the nucleus of the hydrogen, the nucleus is going to be made up, of course, of protons and neutrons. And around the nucleus, we know that we have electrons in there. Now, if that hydrogen is not present next to an electronegative element, then the electrons will stay there. Okay? Nothing is going to take these electrons away. So these electrons are considered to shield the hydrogen from any external field that is applied. So if you apply an external magnetic field and that nucleus is spinning, there are a shield of electrons around it, and these electrons will prevent the magnetic field from reaching that nuclei. So this is why you have to apply a stronger magnetic field in order for that nuclei to feel the magnetic field and the spin. So that causes the signal to appear in the upfield region. So the upfield region is the region where you apply more magnetic field because the nucleus of the hydrogen is far away from the electronegative element. It does have electrons around it. Now, let's say, for example, now if you have your hydrogen next to an electronegative element, next to a chlorine, a bromine, and oxygen, we know that all of these are electronegative elements in there, and the role of the electronegative element is to take electrons away. So it's going to pull electrons. Let's say if I have an oxygen next to a hydrogen, okay? And I am looking at the spinning nuclei of this hydrogen over here. Now I know this oxygen is electronegative element. So that oxygen is going to come and it's going to steal electrons away from the hydrogen. So this is why you're going to have less electrons around the hydrogen in there. When it spins, when you apply a magnetic field and this proton spins, you don't need to apply too much magnetic field for the nucleus of the hydrogen to feel the magnetic field. So this is why that requires less magnetic field to spin, and the signal of the proton is going to appear further downfield. Now, where's the upfield region? Where's the downfield region? It depends one molecule to the other, from one atom to the other. It really depends in there, but take it as a rule. That when a hydrogen is closer to an electronegative element, then it will need a higher magnetic field to spin, and its signal will appear downfield. And when the hydrogen is far away from the electronegative element, it will need more magnetic field, more applied magnetic field to spin, and its signal is going to appear upfield. Let's say if I am given this molecule and I am asked to find out how many proton NMR signals does this molecule have. The rule says that every different hydrogen in a different environment has a signal, meaning that proton A is connected to a bromine. It's different than proton B, which is connected to two CH2s in there. You have to look at all the neighbors that are connected to the proton that is resonating. See a signal for proton A, for proton B, for proton C. All of these are different hydrogens. For proton D, coming to proton E now has, it's basically two CH3s in there. These two CH3s are the same because they are connected to the same CH. So what you're going to see in here is is one signal for proton E. However, that signal, the intensity of the signal is going to correspond to 6 hydrogens. It will be made up of two CH3s. So here, the number of different hydrogens here are going to be 5 different hydrogens. So it's going to be 5 different signals. You're going to see that in the proton NMR. Now the splitting pattern of these signals. The splitting pattern is whenever the hydrogen is resonating, it's spinning. What's going to affect its spinning pattern is the neighboring hydrogen. So that neighboring hydrogen will split the existing hydrogen into n+1 peaks. Let's have an example. So hydrogen A has a neighboring of 2 hydrogens. Hydrogen A is 2 hydrogens, but I don't care about how many hydrogens does it have when I talk about spinning and splitting in this case. I need to look at its neighbor, and its neighbor is hydrogen B. So hydrogen B is 2 hydrogens in there. So I apply the n+1 rule where n is the number of neighboring hydrogens. So I have here 2 hydrogens for B that are spinning. So now these B hydrogens are going to split hydrogen A into 2 plus 1, so it's going to be 3 peaks. The intensity of the 3 peaks is 1 to 2 to 1, so we call this a triplet. So 3 peaks are called a triplet, and we abbreviate it by a small t. Looking at proton B, again, proton B is spinning. So I want to see how many peaks will proton B be split to. So I need to look at its neighbors. And I do have 2 neighbors on this side, 2 neighbors on this side. And these neighbors are also spinning. So they are going to split proton B into 2 plus 2 plus 1. Because n is the number of neighboring hydrogens, and I have 4 hydrogens in there. So it's going to be 5 peaks. I abbreviate 5 peaks as a QU, and this is going to be a quintet. Quintet is 5, and this is the intensity of the peaks that you're going to see. 1 to 4 to 6 to 4 to 1. Now for hydrogen C, it's connected to 2 hydrogens on the side, 1 hydrogen on the side. So this is a 3 neighbors plus 1. So it's going to be 4 peaks. And I'm going to see it as a quartet, and this is the intensity 1 to 3 to 3 to 1. Hydrogen D now, it's connected to a lot of neighbors. It's connected to 3 here, 3 there. Even though these 2 are the same, it doesn't matter. You have to consider them all because all of these hydrogens are spinning. So it's connected to 6 hydrogens on this side, 2 hydrogens on that side, and the other side, and you have to add plus 1, so it's going to be 9 peaks. It's going to be 9 peaks. More than 5 peaks, just go ahead and call this a multiplet. And then hydrogen E is connected to just 1 hydrogen plus 1, so this is going to be a doublet. So the splitting pattern will give me information about the neighboring hydrogens and how many hydrogens do they have. Let's go ahead and draw the proton NMR spectra of this molecule over here. There is on eCampus the proton NMR table. And the proton NMR table, you have 2 tables in there. This is the first one, and this is the second one, and actually there's 3 tables. The first signals normally that you see in the proton NMR, these are the sp3 hybrid carbons. Whether we have a CH3, or we have a CH2, or we have a CH. And this is the order of the hydrogens in the sp3 hybrid carbon. So the CH3s normally appear before the CH2s and then the CH. Now the triple bond are going to show in the upfield region compared to the double bond that is going to show in the downfield region. As long as the signal is shifted further down the spectrum, we're going to call it a downfield region. This is the region where the hydrogen is de-shielded, meaning that it has less electrons around it, so it's going to feel the magnetic field more. So you have your alkene region between 4.5 and 6.5. And then if you have a hydrogen that is connected to the benzene, then it's going to absorb between 6.5 and 8, or it's going to show between 6.5 and 8 parts per million. Now, aldehydes and carboxylic acids are the only carbonyls that are going to show in the proton NMR because these are the ones that have hydrogens. So you're going to end up having your aldehyde, and the aldehyde is going to show at around 10 parts per million. And the acid is going to show at 11 parts per million. It can extend to 12 parts per million, but normally if you see a signal 11 and beyond, this is going to be a carboxylic acid, and it is the hydrogen connected to the oxygen. And if you see a signal at 10 parts per million, then it's going to be that of the aldehyde. Now, both of these signals are going to appear as one peak. So you're going to see them as a singlet. Singlet means one peak. And now, if you have an amine, you are looking at this region in here. The hydrogen that is connected to the nitrogen is going to show between 1 and 3 parts per million, and it depends on the R's that are connected to the nitrogen, how shielded or de-shielded they are. So the more they are de-shielded, the further it is from the 3 parts per million, or the closer it is to the 3 parts per million. And the more they are shielded, the closer it is to the 1 parts per million. Normally, the signal for the NH of the amine is a broad signal. It is not a sharp signal, and you're going to see it like that in the proton NMR between 1 and 3 parts per million. Now, for the alcohol, if you have an alcohol in there, this hydrogen, you're going to see it between 0 and 5 parts per million, and that is going to be a sharp peak. So let's say, for example, if you have a CH3 that is connected to a CH2 that is connected to the OH, and I ask you how many signals are there in the proton NMR? Well, this is going to be proton A, this is going to be proton B. Now, here's the thing. The hydrogen that is connected to the oxygen, this one for simplicity, we don't show any splitting pattern for this hydrogen. Same thing, we don't show any splitting pattern for the hydrogen of the amine. Same thing for the acid and the aldehyde. So all of those are going to appear as one peak no matter how many hydrogens they are connected to. So this is going to be hydrogen C, and this one is going to appear as a singlet. Singlet means one peak. Okay, so you're going to see a one peak, and that one peak is going to be in this region in here. This is a broad region. It depends on the R. What R is that next to the oxygen? Let's go ahead and draw the proton NMR of this molecule here. We said that the closer the hydrogen it is to the electronegative element, the further its signal is going to be shifted downfield. So I'm expecting the proton A to be the furthest downfield. Also, we said that when you're looking at the proton NMR, we said like the first signals that you see in the proton NMR are CH3s, then CH2s, then CHs. This is the order. So the CH will not appear before the CH2. So this means that over here, the CH is going to be the furthest de-shielded among all of those CH2s and CH3s. The one that is going to appear at the beginning of the spectrum are these CH3s that are far away from the bromine. And these CH3s will appear at 0.9 parts per million, and they're going to be a doublet. Doublet because they are connected to one hydrogen, and you're applying the N+1 rule. So this one's going to be 0.9, and we're going to call this this CH3 is going to be a doublet, and it's going to appear at 0.9 parts per million. So when you interpret your proton NMR, you have to put the peak splitting here, comma, and then where it shows as a shift, as a chemical shift in the proton NMR spectra. So this is going to be my CH3. This is the only CH3 in here. And then I'm going to move to the CH2s and then the CH. Now, I'm expecting, as I said, hydrogen A to be furthest downfield. So I'm going to skip that. And then I do have hydrogen C. Hydrogen C is going to be directly next to the double bond because hydrogen C is far away from the bromine. So hydrogen C is going to be split into one hydrogen on this side, two hydrogens on the other side plus one, so it's going to be 4 peaks. So it's going to be quartet, and it is a CH2 in here. And since it is a CH2, it's going to be a little bit shifted further downfield because now it's becoming closer to the bromine. So I'm expecting its signal to be between 1.2 and 1.3 parts per million. Coming to the hydrogen B in here, now I'm coming closer to the bromine. So the signal is going to be shifted now further downfield. But still, I cannot exceed the 1.8 range for the CH3. So just pay attention, or for the sp3 CHs. So this is why my max over here was a 1.7 parts per million. Now the CH2 here is coming closer to the bromine. So this is why now it's showing at 1.4 parts per million. Now next to the CH2, I have hydrogen A. Now I'm forced to put hydrogen A all the way at the end because hydrogen A is directly connected to the bromine. And hydrogen A is going to be a triplet in there because it's connected to 3 hydrogens, and this is how it's going to show. Hydrogen D, it's going to be a multiplet, and it is a CH, and this is where it's going to show, because all of those sp3 hybridization, their signal is going to be between 0.9 and 1.8 parts per million. So the closer the proton is to the electronegative element, the more de-shielded it is. So I'm expecting that proton B to be further down the proton NMR spectrum, and its signal is going to be split into 4 peaks because it's the neighbor of proton A. Proton A, it's going to be a little bit upfield, and its signal is going to be split into 3 peaks. So here I have a combination of a quartet triplet splitting pattern in there, and always a quartet triplet corresponds to an ethyl group. The more electronegative the element is, the further the proton is going to be shifted. So proton B here, since it's connected to a more electronegative element, is going to be further shifted downfield. And the more electronegative elements are there next to the proton, then it's going to also shift that downfield. So I'm expecting proton B to be further shifted downfield than proton A. For benzene, benzene is considered to be an electronegative element. So, or electronegative compound. So benzene normally shows between 6.5 and 8 parts per million. This region is purely for benzene. So if you look at your NMR spectra and see any signal in this region, this means that you have a benzene. Do your DBE. The double bond equivalence of the benzene is 4. So if your DBE is 4 or more, then this means that you have a benzene, especially if you have a signal between 6.5 and 8 parts per million. Benzene exists as monosubstituted, disubstituted, or even more trisubstituted, etc. So if it is more substituted, this means that you have 5 hydrogens in there. That benzene is connected to a group in here. Now, of course, not all these hydrogens are going to be the same. So these 2 hydrogens over here, if we want to label them, this is going to be hydrogen A, this is going to be hydrogen A prime. So these 2 are the same. Hydrogen B and hydrogen B prime are the same, and then you have hydrogen C. So for a monosubstituted benzene, you have 3 different types of hydrogens. And these hydrogens, they're going to split each other. But just for simplicity, we're going to show just 1 peak in there. Just 1 peak that corresponds to all of these 5 hydrogens. But please pay attention that these 5 hydrogens are not the same, and they are going to split each other. Sometimes we show a lot of peaks between 7 and 8, and still the integration goes to 5 hydrogens, so this is a monosubstituted benzene. So when you have a peak or peaks between 7 and 8, and those peaks correspond to a total sum of 5 hydrogens, just know that you are working with a monosubstituted benzene. A disubstituted benzene exists as an ortho, meta, and para, and we said that the ortho is whenever you have positions 1 and 2 occupied on the benzene, meta 1, 3, and para 1, 4. NMR, proton NMR, is useful for the para-substituted benzene, because with the para-substituted benzene, I will have 2 types of hydrogens in there, depending on X and Y. So if X is different than Y, then I'm going to end up having hydrogen A which is going to be equal to hydrogen A prime. So the intensity of the signal for hydrogen A is going to be corresponding to 2 hydrogens. And then I'm going to end up having hydrogen B. Hydrogen B is closer to Y, hydrogen A is closer to X. Assuming X is different than Y, then you're going to have 2 signals in there. Still, we're going to do the N+1 rule. So hydrogen A will be split by hydrogen B into 1 plus 1, so it's going to be a doublet. And hydrogen B will be split by A into another doublet, so you're going to see doublet of doublets. And this is always the case whenever you have a para-substituted benzene. You're going to see 2 doublets in there, and there's a distance between them. Now, whatever doublet that goes further downfield is the one that is connected or closer to the more electronegative element. So let's say, for example, if X is way more electronegative than Y, then hydrogen A or proton A will be further downfield in there. So again, doublet of doublets here is specifically for para-substituted benzene, and I can easily determine this with the proton NMR. Now for the integration of the proton NMR, for these you need to have rulers in there, and I normally will give you the distance value of the integration. So in order to do the integration, you would need the molecular formula. And you will get the molecular formula from the mass spec data. We will talk about it as we proceed. So once you have your molecular formula, you will know exactly how many hydrogens you are working with. Now, you look at your peaks in there in the proton NMR issues, and the integral value is this curved line that you see. So this is the integral line. This is called the integral line in there. Every time you see an integral line, this means that you have a peak. Sometimes the peak, they go into each other. So this is how you know that you are ending with one peak and beginning with a new peak by simply looking or tracing the integral line. So these are the integral lines that you see, and here I have 3 integral lines, so I have 3 peaks. To measure the integration, normally you measure, it's not always that I'm going to give you those values, so you need to measure those yourself. And you can measure them off the screen also. Use a ruler and measure from the bottom of the integral line to the top of the integral line in there. And the units really doesn't matter. You can measure in inches or in centimeter. Measure all of these integral values in there and add those up. So the first thing that you would do, add them up. So add all of those up and you're going to end up getting a number. You take that number and you divide it by the number of hydrogens that you have in your molecular formula. This is why integration cannot happen unless, or you cannot do any integration unless you know your molecular formula. So you divide them by 10 hydrogens in there and you get the number of units per proton. And then you take each number of those and you divide them by the number of units per proton, round to the nearest whole number, and then you will end up getting the number of hydrogens that correspond to every signal. So for example, signal A over here, this is signal A, is going to correspond to 5 hydrogens. I know it's between 7 and 8, so I know that definitely this is a benzene and it's a monosubstituted benzene. Signal 5 corresponds to 2 hydrogens. So if it's 2 hydrogens, then I know that this is a CH2. Okay, again, the integration tells me how many hydrogens does that existing proton have. It doesn't tell me anything about the neighbors. The splitting tells me about the neighbors, but the integration tells me about the existing hydrogens that the proton have. And signal C has 3 hydrogens, which makes sense in there. It is a CH3 and it is the first signal which is upfield. But if you can notice here that the CH3 is further shifted from the 1.8 parts per million because probably you have a lot of oxygens in there and maybe that CH3 is connected to one of these oxygens. This is why it is shifted further downfield. These are the common splitting patterns. I don't want you to memorize, but it's really helpful to know that if you have 2 doublets, then you have 2 hydrogens that are connected to each other. If you have a triplet and a doublet, so a doublet means that the neighbor is 1 hydrogen plus 1. This is going to be a doublet. A triplet means that the neighbor is 2 hydrogens. So always apply the N+1 rule in there. A quartet and a triplet, this really helps because whenever you see them next to each other like this means that you have an ethyl group. A quartet and a doublet means that you have a CH connected to a CH3 because that CH is going to appear as a quartet and that CH3 is going to appear as a doublet. We said that OHs normally, they do not split, they always show as one peak, and the peak is going to be between 2.5 and 3 parts per million. The signal for the aldehyde is going to appear at 10 parts per million and that of the acid between 11 and 12 parts per million. So let's say, for example, if I have this ester and I want to interpret its proton NMR. First of all, the number of signals that I have a signal for CH3. This is proton A, this is proton B, and proton C. So I'm going to see 3 proton NMR signals. Now, of course, there is a big difference between proton C and proton A. Even though both are CH3s, proton C is connected to the CH2. So that is going to show further upfield compared to proton C that is connected to the oxygen. And this is when this table comes in handy. Whenever I have an ester, for example, this is a ketone. This is over here in ester. I have 2 different types of esters. Let's go ahead and label those based on the R that is connected to the, this is a ketone. So I have 2 different types of esters here, okay? And you always look at the R that is connected either to the carbonyl or the oxygen. So here, if I want to look and see what is this shift of this CH3 in here, this is an R connected to an oxygen. So I have to look here. The R is a CH3, so I'm expecting this to be about a 3.7 parts per million. So here, the chemical shift of this guy is going to be around a 3.7 parts per million. And I'm going to see it as a singlet, as a one peak, because next to it there are no hydrogens whatsoever. So that proton A is going to appear as a singlet and it's going to be around a 3.7 parts per million. On the other hand, the proton C, let's go ahead and do the B first because the B is connected to the carbonyl. So proton B is a CH2 and it's connected to the carbonyl. This is still an ester. So I'm going to look at the ester in there. This is going to be the R. The R is connected to a carbonyl now and it is a CH2. So I'm going to see it at around 2.2 parts per million. And that is going to be, look, on this side I don't have any hydrogens, but on this side it's a 3+1, so it's going to be a quartet. So that is going to be a quartet in this case, and it's going to be 2.2 parts per million. And then this CH3 is going to be further upfield. So I'm going to treat this as an R. So if the R is a CH3 in there, it's going to be 0.9 or around like 1 parts per million in this case. So that is going to appear as a triplet, and it's going to be around 1 parts per million. It is a triplet because this hydrogen here is connected to 2 hydrogens plus 1, so it's going to be a triplet in this case. So this table comes in handy by varying the R's to be CH3, CH2s, and CHs, and varying the functional group. So this is a ketone functional group. This is whenever the R is changed into a benzene. These 2 are esters. This is an ether. This is when the R is changed into a benzene in the ether. And then if you have a benzene connected to an R, where R is a CH3, CH2, or CH. And then if you have an alkene and an R, and these are the different R's. So please always look at this chemical shift table in order to determine the chemical shifts of these different hydrogens that belong to these different functional groups. So let's say now if I have this example and you are asked to figure out how many proton NMR signals you have over here. So the rule says that neighboring hydrogens, they split each other if they are a max of 3 sigma bonds far away from each other. They can split each other if they are 2 sigma bonds away from each other. 3 sigma bonds is the max that they can split each other. And we also said that neighboring hydrogens, they are different if they belong to different environments. So I use the term environment in there. And we need this term whenever you have an alkene, because to figure out if these 3 hydrogens are different, you have to look at the environment that they are in, because sometimes it's kind of like misleading in there. So this hydrogen here is different than this hydrogen here, because this hydrogen is simply connected to this carbon, and this hydrogen is connected to this carbon. So we agree that these 2 hydrogens are different. Then these 2 hydrogens are going to split each other. Now coming to these 2 hydrogens here, they belong to the same carbon. And this is completely different than the case where we have something like this. Then when we have like a CH3 that is connected to a CH2. We said that since these 3 hydrogens, they belong to the same carbon, then these 3 hydrogens, they belong to the same environment, so they are all the same. So you're just gonna see one signal for them. This case is different than this case over here. Even though these 2 hydrogens, they belong to the same carbon, but these 2 hydrogens are in different environment. Why? Because this hydrogen here, let me highlight that. This hydrogen here is cis to this hydrogen, okay? And this hydrogen here is a trans to this group. On the other hand, the other hydrogen, which is this one, it's a trans to this hydrogen, and it's cis to this group. So this is why these 2 hydrogens here, they are different because they belong to different environments. To check the different environments on the same carbon, and especially this is around just the alkene, always look at the hydrogens if they are cis or trans to the same groups. If they are cis and trans to the same groups, then they are the same. If they are cis and trans to different groups, then they are different, okay? So these 2 hydrogens are different, so if they are different now, they're going to split each other. So this means that if I'm looking at the proton NMR, I'm going to see a signal for proton A, I'm going to see the signal for proton B, and I'm going to see a signal for proton C, and of course I'm going to see a signal for proton D, so I'm going to see 4 different signals in there. Now the signals for A, B, and C, they are all going to lie, let's pull the table in there, so they're all going to lie in the region of the alkene between 4.5 and 6.5. So you're going to see a lot of peaks in there because that is going to correspond to the 3 peaks. The peaks that you're going to see are the following. So proton A will be split by proton B. Now proton D is far away. It's very far away. So proton D will not split proton A. But whatever is going to split proton A is proton B and the proton C, because proton C is close to A by 3 sigma bonds. This is a sigma, this is a sigma, and this is a sigma. And same thing, proton B is close to A by 3 sigma bonds. So proton A will be split by proton B into a doublet and by proton C into a doublet. So for proton A alone, you're going to see 2 doublets in there. Same thing for B. Proton B also is going to be split into a doublet from proton A and into a doublet from proton C in there. And proton C is going to be the same. You're going to see also 2 doublets for proton A and proton B that are going to split proton C. Now, sometimes these peaks are going to merge with each other, and this is why I said that you're going to see a lot of peaks and those peaks, they are going to appear in the region between 4.5 and 6.5, and they're going to correspond to all of these three different hydrogens.